Okay. There we are. And just in case we need it, here's the calculator. Yep, clear. Okay, so we'll leave it down there. We'll expand this, and we will get to work on today's work. Leaving off where we left off yesterday, the reason you're going to need to know some perfect squares is we're going to be simplifying and finding the exact answer using radicals as needed. That means no decimals, no calculator answers. And here's how you do these. You've got the square root of 20. Well, if I were to take the square root of 20 and do what I said not to do, not that you would, of course, I would say second x squared. That would give me a square root, and then 20, and then enter. Only to discover it's not a perfect square, or a perfect square root, if you will. It is a number with a long, long decimal expansion, and in fact, that decimal expansion goes on forever and can never be made into a fraction. Let's try to math frac it. Math frac, so I hit enter. Enter again. Nope, nothing on earth will make that into a fraction because this is an irrational number. Irrational numbers are not perfect squares. They give decimals that don't even repeat. They're just a jumble of numbers that go on forever. You can round it, but you can't make it into a fraction. So here's what we have to do. Break 20 down into a combination of numbers, factors, that equal 20 when you multiply them, but that include a perfect square. What's a perfect square? A number like 4, because the square root of 4 is 2. So 20 breaks down into 4 times 5. And now, as long as these are multiplied or divided, we can break these down into separate square roots. The square root of 4 times the square root of 5. The square root of 4 is 2, and no radical. But the square root of 5 is an irrational number. It's just the square root of 5, and you can convince yourself of that by taking the square root of 5 on your calculator and finding out that it gives you a long run on decimal, and so it's got to stay this way, and that is the answer. We have simplified the square root of 20. We've pulled out all the perfect squares that are hiding in there so that we can get this down to what actually composes the square root of 20. Let's do it again, the square root of 45. The square root of 45 just gives you a decimal because it's an irrational number, but it does have a perfect square hiding inside it. The square root of 45, well, 45 equals 9 times 5. Equals the square root of 9 times 5 equals the square root of 9 times the square root of 5. The square root of 9 is 3. So we have 3 with no radical times the square root of 5, which is a radical. This is called simplifying radicals. Okay, now here we have the square root of 2 times the square root of 10, which we could easily multiply just directly since they're both square roots. We could say, well, this is the square root of 2 times 10, which is the square root of 20. But doggone it, if we didn't already do the square root of 20, and we know that this is the square root of 4 times 5, which is the square root of 4 times the square root of 5. Well, 4, the square root of 4, equals 2 outside the radical, so your answer is going to be 2 times the square root of 5. But how could you do that so it would be easier to figure out from the beginning? Well, here's the given problem. The square root of 2 times the square root of 10. Break this down completely. 2 is as broken down as it can be. It's the only even prime. But 10 is 2 times 5. So we could break this down into the square root of 2 times the square root of 2 times the square root of 5. And look at that. The square root of 2 times the square root of 2 is the square root of 2 squared, which is 4, times the square root of 5. If you take the square root of something squared, you're going to do this to it. There's a hidden index 2. So we'll have 2 to the 2 over 2 times the square root of 5. Using that rule we talked about yesterday, 2 over 2 is 1. So this is 2 to the 1, which is 2 times the square root of 5. That's another way you could have done this. Okay, the square root of 63. 63 is 9 times 7. The square root of 63 equals the square root of 9 times 7, which is the square root of 9 times the square root of 7. The square root of 9 is 3 times the square root of 7. So see, now you see the reasons for having to learn your times tables in elementary school. A long time ago, I know. And you can get so used to using a calculator, you completely forget, those numbers, which is why I'm providing you with the charts. Again, it's going to be in modules, but it's not completely there yet. Okay, let's take the square root of 250. Now 250, anytime you have a 0 on the end, that means it's the first numbers times 10. So 250 is 25 times 10. And 25 is a perfect square. So this is very convenient. 25 times 10 equals the square root of 25 times the square root of 10. Well, the square root of 10 just breaks down into 2 times 5. 2 is not a perfect square. 5 is not a perfect square. So but 25 is because you can take a nice square root from it. The square root of 25 is 5. So 5 times the square root of 10 is your answer. And, okay, so you've got to be able to do that, and as you can see, soon you're going to really need to be able to do that. So start getting good at it now. Okay, now we're going to divide and simplify. What does that mean? Well, here it means you have a square root divided by a square root. So you can make one big square root and say, well, okay, well, this is the same as the square root of 18 over 2, which is the square root of 9. You know what the square root of 9 is. It's 3. So the square root of 18 divided by the square root of 2 can be changed into the square root of 18 over 2. It gives you the square root of 9, and the square root of 9 is 3. The principal square root of 9 is 3. So you can do that also. It's handy when you have the same kind of root. But adding and subtracting is not that easy. On the surface, there is nothing you can do with this, because the only time you can add square roots or any kind of root is if you have the square root, something like this, the square root of 3, maybe 2 times the square root of 3, plus 5 times the square root of 3. I can add these. The answer is 8 times the square root of 3, because these are exactly the same kind of root with exactly the same kind of number. Well,
don't you mean 7?
2 times, yeah, I do actually. Doggone it. Thank you. There you go. So I have 2 square roots of 3. I add 5 square roots of 3. That means I have 7 square roots of 3 altogether. But why I can do that is that these are exactly the same kind of radical, square roots, and they are exactly the same radicand, the number underneath the radical. So these are said to be like terms, or like radicals. And when you've got like radicals, you can add them. These are not like radicals. It looks like you cannot add them. Ah, but don't take anything on face value. 72 is 9 times 8. It's got a perfect square in it. In fact, 8 has a perfect square in it. Let's break down 72. 72, my initial reaction is to say, well, that's 9 times 8, which is true. And 9 is a perfect square, a PS, a perfect square. But there is a perfect square hiding in 8. It's 4. So I'm going to get rid of 8. And I'm going to say, well, this is going to be 9 times 4 times 2, because 8 is 4 times 2. Now I have the perfect square 9 times the perfect square 4. But look at what happens. 9 times 4 is 36. 36 times 2. 36 is a perfect square. The square root of 36 is 6. So now I know that a better choice than 9 times 8 for 72 would have been 9 times 4 times 2, which is 36 times 2. So let's look at the square root of 72. The square root of 72 equals the square root of 36 times 2 equals the square root of 36 times the square root of 2 equals, because the square root of 36 is 6, times the square root of 2. Now let's look at 32 and do the same thing. I am most familiar with using 32 equals 8 times 4. But 8 equals 2 times 4, and 4 is a perfect square. So 8 is 2 times 4, and then there's times 4. 2 times 4 times 4 equals 32. But 4 times 4 is a perfect square. It's 16, and the square root of 16 is 4. So let's look at the square root of 32 in this new light. 32 also equals 16 times 2. So the square root of 32 equals the square root of 16 times 2, which is the square root of 16 times the square root of 2, which is 4 times the square root of 2. So now, since the problem is 7 times the square root of 72, that means I've got 7 times. The square root of 72 is 6 times the square root of 2. So I've got 7 times 6 times the square root of 2 plus 6 times the square root of 32, and the square root of 32 is 4 times the square root of 2. I didn't need to write it that way. So 7 times 6 is 42, times the square root of 2, plus 6 times 4 is 24, so that'll be 24 times the square root of 2. And now I'm about to run out of room. I'll do it this way. So how many square roots of 2 do I have? I have 42 plus 24 square roots of 2. So 2 plus 4 is 6, and 4 plus 2 is 6. So if I'm not mistaken, I have 66 square roots of 2. They tried to fool us, but we're so smart we cannot be fooled. I hope. This is called adding and simplifying. You cannot just take on face value that you can't add 2 square roots just because they look different in the beginning. You've got to break them down and find out. So I'm going to write it bigger down here. 7 times the square root of 72 plus 6 times the square root of 32 equals 66 square roots of 2, or 66 times the square root of 2. Okay, we're going to do the same kind of thing over here. I'm going to look at the square root of 48. I'm going to look at the square root of 12. And I'm going to look at the square root of 300. Don't let hundreds scare you. This is really 3 times 100. And 100 is a perfect square. So that's actually going to be the easiest number to break down. So we've got the square root of 48. And as it is, I do already know that 48 equals 16 times 3. But what if you didn't? What is the most common number that 48 equals? Well, when I think of 48, I think of taking a drink. There. Excuse me. I think of something that all of us learned in pre-algebra. I'm going to erase the square root of 48. No, I'm not. What I'm going to do is this. I'm going to mark through it because it'll be too hard, maybe, excuse me, to break this down. But here's what we can do. 48 is an even number, so you know that 2 goes into it evenly. You might even be able to see that 4 goes into it evenly. Oh, because 4 goes into 4 and 4 goes into 8. Yes, okay. 48 equals 4 times 12. 4 is 2 times 2, and that's why it's a perfect square. 12 equals 4 times 3. And 4 is 2 times 2, which is why it's a perfect square. It's 2 squared. And in fact, a perfect square times a perfect square gives you a perfect square. That's why 14 is a perfect square, because it's 4 times 4, which is 4 squared. So I can see now that 48 is going to equal 16 times 3 if I could not see it before, and that 16 is a perfect square. Okay, pretty smart. So let's come down here and write it this way. The square root of 48 equals the square root of 16 times 3 equals the square root of 16 times the square root of 3, and the square root of 16 is 4. So the square root of 48 is 4 times the square root of 3. Now let's break down the square root of 12, right here. Well, this is a little easier. The square root of 12 is, of course, 4 times 3, or 3 times 4. So the square root of 12 is 2 times the square root of 3. And like I said, 300 is 3 times 100. So this one is a kind of a gimme, okay? The square root of 300 equals the square root of 3 times 100, and 100 is 10 times 10, a perfect square. So that's going to equal the square root of 3 times the square root of 100. The square root of 100 is 10, so you've got the square root of 3 times 10, which is 10 times the square root of 3. But now I'm going to write it in a more organized, neat fashion. The square root of 300 equals, I'm going to put the 100 in front just because it's easier. That's my perfect square. Equals the square root of 100 times the square root of 3. And this is 10 times the square root of 3. So now, the square root of 48 is 4 times the square root of 3. So 2 times the square root of 48, let me write it up here, is 2 times 4 times the square root of 3. Minus 2 times the square root of 3, because that's what the square root of 12 is, 2 times the square root of 3, plus 7 times the square root of 300, which is 10 times the square root of 3. So I'm going to have 8 times the square root of 3 minus 2 times the square root of 3 plus 70 times the square root of 3. Well, let's see. I've got 8 square roots of 3. I take away 2 square roots of 3. That gives me 6 square roots of 3. So I have 6 square roots of 3 plus 70 square roots of 3. That will be 76 square roots of 3, just to put it over here in the little box. But I'll write it there also. 76 square roots of 3, or 76 times the square root of 3. It takes detective work. Okay, so much for addition. Now we're going to multiply. Yeah, okay. This is like a binomial, although technically it's not a binomial. A binomial is a polynomial. This is not a polynomial. Nonetheless, this is 2 different terms added together, multiplied by those same terms subtracted. And so we're going to multiply. The square root of 11 times the square root of 11 minus the square root of 11 times the square root of 17 plus the square root of 17 times the square root of 11 plus the square root of 17 times negative the square root of 17. So here's what that'll give us. The square root of 11 times the square root of 11 minus the square root of 11 times the square root of 17 plus the square root of 17 times the square root of 11 you've got a plus square root of 17 times a minus square root of 17. What that gives you is a minus, because plus times minus is minus, the square root of 17 times the square root of 17. Now, we can do this. This is going to be the square root of 11 times 11. Actually, it's 11 squared, isn't it? 11 times 11 is 11 squared. Minus, I have no idea, 17 times 11. No, 17 times 11. There. 187. Okay, so minus the square root of 187 plus the square root of 187 minus the square root of 17 times 17, which is 17 squared. The rest of this is really easy to do by hand, because look what happens. You've got minus the square root of 87 plus the square root of 87, which is the square root of 187 minus the square root of 187. That's 0. Meanwhile, the square root of something squared is the something. The square root of 11 squared is 11. And you've got minus the square root of 17 squared. Well, the square root of 17 squared is 17. So you have 11 plus 0 minus 17, which is 11 minus 17, and that equals negative 6. So that horrible looking thing really just equals negative 6. Now, if you take a minute and notice, if you let the square root of 11 equal a, and the square root of 17 equal b, then this is in the form of a plus b times a minus b. These are conjugates. When you multiply conjugates together, the middle terms fall out. But the catch is the first terms have to be exactly alike. The second terms have to be exactly alike. and the signs have to be opposite. The signs in the middle. If you have that, then your answer is a squared minus b squared. And as you already know, this can be factored by the difference of two squares into a plus b times a minus b. So when you know you're multiplying conjugates, a much quicker way to do this would be this. The square root of 11 squared minus the square root of 17 squared. Well, when you square a square root, you get what's underneath. When you square a square root, you get what's underneath. Since they're positive numbers. 11 is positive, 17 is positive. Yes, there's a minus sign between them, but that cannot affect a number under a radical. So that would give us the square root of 11 squared is 11. The square root of 17 squared is 17. 11 minus 17 is negative 6. It's taken you all of 1 minute to do this. But you're always free to do it the longer way. Okay, now here, both of these, that one and that one, these are much simpler problems because look, here's a number times terms in parentheses. All I have to do is distribution. The square root of 6 times 7 minus the square root of 6 times 6 times the square root of 6. Let's see what that gives us. The square root of 6 times 7 is 7 times the square root of 6. We always put the number outside the radical in front of the number in the radical. Okay, and then there's a minus sign. This is positive, so we'll keep our minus sign. We're going to have 6 times the square root of 6 times the square root of 6. This is 7 times the square root of 6 minus 6 times the square root of 6 squared. This is going to be 7 times the square root of 6 minus 6 times the square root of 6 squared is 6. So our answer is going to be 7 times the square root of 6 minus 36. And that's as small as we can get. We can't combine those terms because they're not like terms. This is a radical term, a square root term, and this is just a constant. They're not the same kind of term, so we have to leave our answer as 7 times the square root of 6 minus 36. When we're working with an exact answer. So you have to obey the blue instructions and the top instructions, both of them. Now this is the same exact kind of problem. You've got the square root of 11 times 7 minus the square root of 11 times 3 times the square root of 11. So you're going to have 7 times the square root of 11 minus 3 times the square root of 11 times the square root of 11, which will be 7 times the square root of 11 minus 3 times the square root of 11 squared, which will be 7 times the square root of 11 minus 3 times 11. So you will have 7 times the square root of 11 minus 31. Same kind of answer. They have to stay separate for the same reason. One is a radical term, one is a constant term, not the same kind of terms. But this one is dangerous, really, really dangerous. This is what you want. What you want. Which is wrong. But this is what you want. 3 squared plus the square root of 2 squared is going to be 9 plus 2 is 11. You're done until you see that the answer is wrong. Wrong. Let's make it red. Blech. Wrong. No, unfortunately, there's a plus sign there. That stops you from having any fun. So would a minus sign. It means you've got two different terms. They are not multiplied by each other. So you can't just square both numbers. Instead, you are going to have to do this. The square root of 3 plus the square root of 2 times 3 plus the square root of 2. Now you still have to beware because we just did conjugate problems back here. A conjugate problem. Those aren't conjugates. They don't have opposite signs between them. They have the same exact sign between them. So you can't say, oh, well, this is 9 minus 2, which is 7. Not. Instead, you're going to have to multiply the 3 times the 3 and 3 times the square root of 2. The square root of 2 times 3, the square root of 2 times 2. So that this is what you have. You have 3 times 3 plus 3 times the square root of 2 plus, I could say the square root of 2 times 3, but we write it the other way, 3 times the square root of 2 plus the square root of 2 times the square root of 2. So this is going to be 9 plus, now this is addition. I've got 3 square roots of 2 plus another 3 square roots of 2. That means I have 6 square roots of 2 plus the square root of 2 times the square root of 2. We could go to another step and say this is the square root of 2 squared, so that you'll have 9 plus 6 times the square root of 2 plus 2. Now 9 is a constant and 2 is a constant, so you can combine them. You'll have 9 plus 2 plus 6 times the square root of 2, and that's going to equal 11 plus 6 times the square root of 2. So you have to be very, very careful. Now, after I say that, notice what the next problem is. You've got a square root of 10 and a square root of 10. You've got a square root of 6, you've got a square root of 6. You have a minus, you have a plus. These are conjugates. And so you can take the quicker root, which is the square root of 10 squared minus the square root of 6 squared, which will be 10 minus 6, which will be 4. Yeah, or you can do it the long way. The square root of 10 times the square root of 10, the square root of 10 times the square root of 6, the square minus the square root of 6 times the square root of 10, minus the square root of 6 times plus the square root of 6. And so that would give you the square root of 10 times the square root of 10 plus the square root of 10 times 10 times square root of 10 times the square root of 6 minus the square root of 6 times the square root of 10 minus times plus is minus the square root of 6 times the square root of 6. So this would be the square root of 10 squared plus the square root of 60 minus the square root of 60 minus the square root of 6 squared. The square root of 60 minus the square root of 60 is 0. The square root of 10 squared is 10. The square root of 6 squared is 6. So you have 10 minus 6, which is 4. Either way, 4 is the answer. So you have a choice with conjugates. You can do them the long way. You can do them the short way. If you do them the short way, you're gambling that yes, you're right, they are conjugates. On the other hand, if you do them the long way, if you end up without having conjugates, that is not having conjugates, you'll get the answer right. So it's probably safer to do it the long way. This is that same kind of problem. They're conjugates. No, they're not. I would have gotten it wrong. They are not conjugates. This is 3 times the square root of 6. This is 5 times the square root of 6. They're not even the same first term or the same second term. On the other hand, I think you get the idea, and I want to go into something that really takes some time to talk about. You did talk about the first part of what we're doing. You talked about that a little bit in beginning algebra, or you should have. You're supposed to have. On the other hand, teachers drop it all the time when you run out of time. But now we have to talk about it seriously. This is wrong, not because there's something wrong with the answer, but because it's written the wrong way. This is the square root of 17 over the square root of 3. And technically, you're not allowed to have any kind of root sign. Square root, cube root, fourth root, fifth root, sixth root, any kind of root sign in the denominator. So we have to go through a process called rationalizing the denominator. To rationalize the denominator means you make it a rational number and not an irrational number. Is an irrational number. Here's the process you use with square roots, which are always the easiest to deal with. The square root of 17 over the square root of 3 times 1. Well, we all know that if you multiply the square root of 17 over the square root of 3 or any number by 1, you just get the same number. But you can change the form when you multiply by 1. For instance, I know back when there were dinosaurs when I was a child, we had this joke called, "Hey, kidneys, I got kidneys." I don't know if kids still use that or not. Probably not. I happen to know, this is aside, like in Shakespeare, you go aside and you say something. Well, I happen to know that the square root of 3 times the square root of 3 is the square root of 9, which is 3. I could also have called it the square root of 3 squared, which is 3. You can do it either way. Well, what if I chose a very convenient form of 1? This. Anytime you have a fraction with exactly the same thing in the numerator and in the denominator, that's 1. But now here's my plan. I'm going to multiply the bottoms together, the denominators, and I'm going to multiply the tops together, the numerators. That will give me the square root of 17 times 3 over the square root of 3 times 3. How about that? Now, I believe the square root of 17 times 3 is the square root of 51, I think. 3 times, yes, it is. Over the square root of 3 squared. Well, the square root of 3 squared is 3. So our answer is the square root of 51 over 3. Now, I am going to take time to do something for you just to prove to you, clear, that the square root of 17 over 3 equals the same exact thing as the square root of 17 divided by the square root of 3. They equal each other, and they equal exactly what this equals. They equal the same number, but it's a different form. Let's do it. Okay. Pull that all the way out. The square root of 17 divided by 3. Hit the right arrow key. Now I'm going to say enter. There's what it equals. Okay, now the square root of 17. Hit the right arrow key to come to the outside of the radical, divided by the square root of 3, come to the right side of the radical if you've got this kind of calculator. If not, you close the parentheses. And then you hit enter. Same exact number, look at that. Now I'm going to divide the square root of 51 by 3. Right, okay. Now I have to move to the outside. Look what would happen if I just said divide by 3. I mean, that would be all wrong. So I can't say that. Clear. No, delete. Delete. I'm going to hit the right arrow key and move to the outside of the radical. Then I divide. Then I divide by 3. Because remember, it's not the square root of 3 on the bottom now. It's 3. Enter. Same exact number. So you might say, really the way I say, how silly. How silly is that? Why do you have to do that? And the answer is you do. So just be good. Okay, clear. Where's clear? There's clear. Okay. We're going to do it again, the exact same kind of problem. The square root of 11 over 2 equals the square root of 11 over the square root of 2. But there's a radical on the bottom. Oh no! Well, that's going to equal the square root of 11 over the square root of 2 times 1 in the form of the square root of 2 over the square root of 2. Then I multiply the numerators together and get the square root of 22. And I multiply the denominators together, get the square root of 2 squared, or we could just say 4, because everybody and their uncle knows the square root of 4 is 2. So the square root of 22 over just 2. Now, I need to tell you that you cannot divide the square root of 22 by 2. These two numbers cannot communicate in any way. It's like being in jail in solitary confinement. You're not getting to number 22, no matter what you do. So neither is number 2. This is the answer, the final answer. Okay. Now we get to the hard ones. And I don't think you've done this before. Everything we've done so far is part of intermediate algebra. Even that. Well, that's part of beginning algebra. It really is. And a lot of this actually you would have talked about in beginning algebra, but it's not emphasized. Sometimes it's not even put on the final exam. This is college algebra. We're going to rationalize this denominator, but it has 2 terms. You have to use a completely different method. Here's the method. I am going to multiply by 1. But here's the form it's going to take. the conjugate of 5 minus the square root of 6, which is 5 plus the square root of 6. Okay, this then will be 2 times 5 plus the square root of 6, because we multiply the two tops together, over 5 minus the square root of 6 times 5 plus the square root of 6. So you're going to have 10 minus 2 times the square root of 6 over 5 squared minus the square root of 6 squared. So it will be, the answer will be 10 minus 2 times the square root of 6 over 25 minus 6, 6, equals 10 minus 2 times the square root of 6 over 19.
Miss Barbara,
Yes,
why is it 10 minus 2 on the top?
it should have been a plus. Doggone it. Okay, so 2 points off for a sign error. There it is. You're right. I have no idea why I did that. I think because I was planning on doing that and thinking about minusing the square minus the square, and it translated. So everybody needs to be careful about that, especially when your brain is working ahead of your body. That's a major problem for teachers because they already know how it's going to end up. And so they make little mistakes because their brain is moving faster than their hand. Thank you. Always tell me, thank you. Okay, but anyway, that is the answer.
And could you not add 10 and 2 together, or is it because 2 is part of the square root of 6 variable?
Yes, yes,
Okay.
very good. This is a constant, and this is a radical term. But there is something I really should not have done. And that is I should have left it like this. Because what if the answer had been a little bit different and I had had 18 down here? Then I could have canceled the 2 into the 18 and had 9. And my math lab would count it wrong. So you don't have to multiply these two factors together unless you're told to do it. Or if you want to wait to do it to see if something up there could cancel out. Now, as it is, I'm lucky because the 2 will not go evenly into the 19. But again, if it had been an even number, I'd be sunk. Not only a sign error, but another error on top of it. So good. Let's do this. 6 plus the square root of 7 over the square root of 3 plus the square root of 7. Now I have to rationalize the denominator. Times the conjugate of this, which will be the square root of 3 and the square root of 7, but this is a plus, so this has got to be a minus. Okay, I actually am going to go ahead and multiply the tops together when they're like this. Let's see. I might find out I was wrong. There, and there, and there, and there. Six times the square root of 3 minus 6 times the square root of 7 plus the square root of 21 minus the square root of 7 squared. Over. I'm not going to have any kind of common factor, so I don't need to worry. Famous last words, right? But no, I don't. Here's the strategy for this when you know for sure you're multiplying conjugates. Put the square root of 3 in there and the square root of 7 in here. Cool, so I'll come over here. This is 6 times the square root of 3 minus 6 times the square root of 7 plus the square root of 21 minus 7 over 3 minus 7. Well, having a negative denominator causes its own problems, as you will see, but we can deal with it. Maybe. I can't leave it like that because you know and I know that my math lab does not like negative numbers on the bottom. In fact, neither do math teachers, but my math lab likes it even less. My math lab counts the whole thing wrong for it, whereas I probably would not. Here's what you have to do when you get a negative number in the denominator. You already know, you pull it out in front. But now you've got all these terms. Wait and see what you have to do. The first thing I'm going to do is take this minus sign and bring it out here in front. So negative 6 times the square root of 3 minus 6 times the square root of 7 plus the square root of 21 minus 7 over 4. Now we're not going to leave it that way because nice people don't do it. That negative sign is going to change position one more time. In fact, you could skip this step completely, but I wanted to show it to you. This is going to be negative parentheses 6 times the square root of 3 minus 6 times the square root of 7 plus the square root of 21 minus 7 over positive 4. Okay, now remember learning that when you've got a negative in front of parentheses, it acts like a -1. And you multiply every term on the inside. So, finally, getting to the end of this, negative 6 times the square root of 3. Negative times negative is positive, so that'll be a plus. 6 times the square root of 7. Negative times positive is negative, so minus the square root of 21. Negative times negative is minus times minus is plus, or negative times negative is positive. 7 all over positive 4, and that is your answer. Yay, me! If I didn't make some other embarrassing little error. I don't think I did this time. I was really watching myself. How about that for a nice way to spend the morning? We're done! Two minutes early. Okay, now 1 minute early.
Are we good?
Yeah,
Okay, just wanted to make sure. Have a nice day.
you
Have a
too.
great day.
Thank you.